Hello, my name is Zach Schemel, and today I'll be presenting my final project on thermal installation and fire protection. So, conventional fireproofing, or a touch of history, basically consisted of using clay, gravel, sand, and other inert materials to either coat the outsides of buildings or fill the air spaces in walls, both to insulate and trap heat in, to keep buildings warm in the winter, but also to have an inert high heat resistance material that would effectively limit flame spread. The endpoint of what a lot of people would consider old school fireproofing ended when THPC was invented in 1953. This is a chemical that is used to treat fabrics that make them far more flame resistant. And this is really the first of the sort of materials revolution that happened after the 1940s and 50s that revolutionized the world of fireproofing. So modern fireproofing is all from this material revolution. It first includes things like intumescent paint, which can be seen down here. This is a type of paint that when heat is applied to it, drastically, it breaks down the polymers that it's made of, and it drastically increases the volume and decreases the density of the material. This traps air inside, which, because air is such a bad transmitter of heat, actually means that it is much more effective at reducing the amount of heat that is transferred through the material and into the steel or other structural beam underneath. This can also happen with things like sodium silicate, which has a similar purpose, and that is a very bad transmitter of heat and will be used to coat important structural components of buildings. There's also things like concrete and drywall, which in a way are the most evolved forms of the old gravel and clay that was used in ancient times. Gypsum is most commonly used in drywall, and concrete and things like cinder blocks. So in home design, the main goal is to reduce the flame spread. Most drywall to this effect is rated to 10 minutes. The goal is not necessarily to save the structure. Building a building that is, or a commercial home, not a commercial home, but a private home that is almost completely flame resistant or has long-term rated firewalls in it would be prohibitively expensive. The main goal is to give things like smoke detectors time to activate, warn people that there is a fire, and for people to evacuate the building and get out safely. Cinder blocks, for this reason, are becoming increasingly common. Cinder blocks do very well at maintaining structural integrity, which we'll see in a minute after heat or during or while being heated. And they're also very cheap and are very good at reducing flame spread because they are very poor conductors of heat. So touching on what I just mentioned a little bit with some of the theoretical side, here we see thermal resistance values for things like plasterboard and various densities of cellular concrete, which is basically concrete that's fashioned sort of like a styrofoam with air pockets trapped inside of it. This is what cinder blocks are most typically made out of. And as I was touching on earlier, you can see steel and concrete both lose structural integrity as a result of temperature, but whereby 400 or 500 degrees Celsius, the structural steel is already down to about 30% of its initial strength. The concrete is still at about 80% of its initial strength. And for it to even get down to 40%, it requires almost double the temperature that steel does. So that's another reason why concrete's becoming more common. But all materials lose heat or lose structural stability or integrity as heated, like this. This phenomena is actually what caused the steel in the World Trade Centers to give out and then to collapse. So this is why things like steel beams especially are coated with paints and treatments that reduce the amount of heat that will actually be exposed to them. And this here is just showing how a wall in interior and exterior walls in homes are made up of many different layers and geometries of materials. And it is important to do testing to understand how those materials function together. An example where this was not properly done was in England. There was a fire in a apartment building that a new layer of eco-friendly um, insulation had been added to the outside of the building, and it had never been tested with the actual material of the building wall. And what was found is that when there was a fire, a relatively small fire in one apartment, it allowed and trapped in the hot gases and allowed the hot gases from that fire to run up and down the building and ignite the entire building in a very, very short period of time because it had never been tested with the existing geometry of the wall. So, going on to what I was just talking about, improving it,
So this is
here
just a
is an
standard
example,
piece of
or
material.
actually, I'll show the cinder block first. This is a cinder
So
block,
we
and
just
I've been
hit
holding this
10
propane
minutes
torch
of
by the
the
time this video has
blowtorch
been taken
on
against this side of
the
the cinder block for
outside.
about 10 minutes. You can see
So
the
we're going to
discoloration.
set that to the
When we
side.
take the torch off of it and we get a read on the thermometer, remember, this is after about 10 minutes of continuous heating.
And then
The
get
outside of
a
this cinder
heat
block
reading from over here. So right where it was being
is at
held,
about
it's
its
about
hottest, is
300 degrees
about
C.
370 degrees. That's about the hottest reading you
And
see on that.
the inside,
The
that same
cold side
spot,
never gets higher than
about 70 to
87
80
degrees C after
degrees
10
C.
minutes of a propane torch held against it. And a propane torch, and that's small, if it was scaled up, the release rate per area of the heat release rate, if you will, of that propane torch is roughly equivalent to a fully developed room fire if you were to scale up the per area release rate, the flux of energy coming out of that propane torch. So that's a pretty good demonstrator of just how little heat will be transferred through that. And remember, there is still this whole air pocket in the middle that would have to be heated, and then the other wall would have to be heated, and only then can the opposite side of that wall begin to heat. Showing the
Drywall,
same or a
and
similar
demonstrate just
demonstration
how
with
poor
plasterboard,
its heat resistance is.
and I'm going to
I'm not
hold
even
this
going
propane
to
torch against it for less
cut
than 30
straight to when we
seconds,
are 10 minutes in.
and we're going to see
I'm
the
going to hold
immediate
this
discoloration.
blowtorch about
Now,
an inch away
while it's waited the 10 minutes
for
before
less than 30
falls
seconds.
apart, it will get hot enough on the other side of that for things like dirty clothes, mattresses, or cushioned chairs to begin to smolder and
Pull that
ignite
back.
much before that. So as you can see, that was less than 30 seconds of
Shut
heating,
this off.
making sure to turn the propane torch off.
And then we're
And we're
going
going
to
to
go
read the
in with
temperature
the
on this side.
heat on
As you
this
can see, it
side.
gets up
It's
to
about
about
180 right at the
173, I
epicenter of
think is
that.
the hottest.
And right here on the back side,
And
as you
on the
can
cold
see,
side,
it is already
it's
climbed to
already at one
53 degrees
point
C.
up
And
into
ambient
the
temperature
high 50s and low
is just under
60s
30 C.
in less than 30 seconds, whereas to get to the mid 80s took a cinder block over 10 minutes of continual exposure to the heat, which is just a good demonstration of how various materials stand up to heat and are better or worse at absorbing and transferring heat differently.
So we just hit
Oh, there we go. Thank you.